for Neumann entropy as a measure of the information content of a quantum source. And then I showed you several ways in which this notion proves to be very useful. One of which was trying to decode information that is classical information that is encoded into quantum states. You saw the Holevo bound, something that is very, very useful in many contexts. You might even see it again today in the course of this talk. Then I also, I've just repeated what I said earlier, that von Neumann entropy can be viewed as the incompressible information that is contained in a source that produces random superpositions. Right? So today's talk is going to be just as it's going to again touch on only a very small number of topics, and try to give you a flavor of results in those topics. So the two topics that I'll be focusing on will be quantum error correction. I'll start by reviewing what David told us about yesterday, and then show you a couple of new things about the extra quantum resources that are required for quantum error correction. Those will employ, again, these tools from information theory, namely von Neumann entropy and its properties. And then I'll go on to another notion that is very peculiar, very unique to quantum computation, and that is of entanglement. I'll try to show you a couple of examples of where it comes up, try to give you a sense of what it is for a state to be entangled, and then try to come up with a measure of how entangled a certain state is, and finally give some applications, or just sketch some applications of the results that come up as we study those questions. Okay, so yesterday we saw perhaps for the first time what a realistic quantum memory might look like, and we saw that such a quantum memory cannot store information that is isolated from the environment for indefinite periods of time. In fact, quantum information is really very, very sensitive to all external factors, and errors are very, very easy to occur by this interaction with the surroundings. And moreover, errors are also introduced during the course of a computation through the use of faulty gates that we cannot hope to even implement exactly, or also measurements that we might perform during a computation. However, we might hope that there is a way we might be able to engineer a system, a quantum memory, to be reasonably immune to those errors. And we saw one such reasonable consequence could be that errors that occur are quite local, that they occur in a few qubits or one qubit at a time, and also that perhaps not too many of these qubits are prone to error, right? So during the course of this talk, I'll be assuming, just to set the notation right away, that we'll be dealing with a quantum memory consisting of n qubits, t of which are susceptible to error. Then we saw two examples of possible quantum errors. One that is quite familiar to us from the classical world, which is the bit flip, which would take a superposition like so to a state with the 0 and the 1 exchanged. Right? And we also saw this this kind of error called a phase flip, which is very specific to quantum computation. There's no classical analog of it. And this flips the sign of the amplitude of the one state. Okay. As you've seen, handling bit errors is quite straightforward. There's only one subtlety, right, which I'll just highlight in a moment. But the main idea was that you could use a classical error correcting code for handling such errors. You could encode a 0, for example, by a repetition code, and a 1 similarly by a string of 3 ones. And then you could detect any bit flip error by comparing all the bits, right? And of course you could then correct it. So the main point in this error correcting procedure is that one is not looking directly at the state, at the state that is written down. You're not making a measurement to see whether your state is 0, 0, 0, which is one of the uncorrupted states, or whether it's 1, 1, 1 or 1, 1, 0, which is one of the corrupted states. But what you're trying to do is to isolate only the type of error that has occurred, right? And the point there is that in general, the state that is encoded is a superposition of your classical basis states 0 and 1. And we really don't want to disturb that quantum superposition by looking at what state, what classical basis state was sitting in there, right? So by writing out only the error that occurred and undoing that error, we are preserving the quantum superposition that we started out with. Okay. So that was probably the only difference from a classical error correction procedure. Now, handling phase errors was required a few more tricks, a few more quantum tricks, in fact, right? And the main observation there was that although you couldn't tell just by looking at the contents of your memory, that is, by looking at the bit strings that were stored there, whether or not a phase flip occurred, you could instead look at your quantum memory in this rotated basis, the Hadamard basis, right? And in that basis, every phase flip error looks like a bit flip, right? Every logical 0 looks like a logical 1. And so in this transformed basis, if we had a state that was a classical error correcting code, right, such as this, the 0 plus 1 state, which is the 0 in the Hadamard basis, tensored 3 times, any phase flip could be corrected by doing a Hadamard transform and observing that one of the bits was different from the other two, right? So we could handle these simple errors. How about more general arbitrary errors on one qubit? And yet again, it's really a very surprising thing that handling just those two simple kinds of error, one could deal with all possible one qubit errors, right? And a sketch of the argument goes as follows. The effect of any arbitrary error on one qubit can be represented by as follows. What it basically does is it takes a quantum superposition to a mixture of states where each state is the original one transformed by some linear transformation AI, right? So the density matrix basically goes from rho to rho conjugated with AI summed up over all I. And furthermore, every such AI, let's say in the one qubit case, can be written out in terms of these bit or phase flip operators, right? So all these operators, the 4 Pauli operators, form a basis for 1 qubit matrices, right? And of course, one could generalize this to many more qubits. Again, each AI acting on, let's say, n qubits now, could be written out as a tensor product of a sequence of these matrices. Okay. So we're all set to look at the main construction that was shown yesterday. And yeah. Right. Oh, okay. Thank you. Thank you. It's yeah. The reason that I didn't bother to explain how the this fourth kind of error out here is handled is because this is basically these two errors composed with each other with an additional phase factor. So sigma y is I times sigma x times sigma z. Okay? So if one can handle bit and phase errors simultaneously on a qubit, then one can also handle the sigma y error. Okay, the simultaneous bit and phase flip. Okay. So back to the Caldebank-Shor-Stein construction. So the main idea behind this construction is in fact something that you've seen repeatedly in the design of quantum algorithms, right? That if you had a very special kind of superposition, a very special kind of wave that consisted of basically a uniform superposition over all elements of a subgroup of, let's say, z2 to the n, then if you did a Fourier transform, in this case the Hadamard transform tensored n times, then what you end up with is a uniform superposition over the perp subgroup. Okay, so in this case the perp subgroup is basically the dual of this subgroup, meaning it consists of all the vectors in z2 to the n, which are perpendicular to it according to the scalar product in z2. So this is xi, ui, summed over all I, mod 2. Okay, so I've dropped out normalization constants as has been the tradition in this workshop. Okay, so how does this help us construct a quantum code? Basically, if all you have to notice is that if both C, that is all these U's that belong to C, and C perp, that is all V belonging to C perp, were actually code words from suitable error correcting codes, in this case, let's say NKD, classical linear error correcting codes, then we could correct up to T phase and bit errors, right? T here being D minus 1 over 2. And the reason is simple. Bit flips can be handled because all these basis states are actually states from a classical error correcting code, right? And then phase flips can be handled because after you do this Hadamard transform, which converts these phase flips to bit flips, which appear as errors in these strings, they can also be corrected because of the property of error correcting property of C perp, right? So indeed, we have constructed one state that is quite robust against errors. Well, the natural step is to